Welcome back, everyone. So, in the last lecture, we have seen what are determinants and adjoint. So, today we are going to, I'm going to teach a very important topic, which is vector spaces and subspaces. So, this is one of the most important topics in linear algebra. Not just from gate point of view, but also like if you are a machine learning engineer or want to become a machine learning engineer or a researcher, then you should have a good idea of what are vector spaces and subspaces, because many machine learning algorithms has this application of vector subspaces. All right. So So the first, we will first see what are vector spaces, and then we will see what are vector subspaces. So for vector spaces, there is one requirement is that all linear combinations must stay in this vector space. That is, all linear combinations C times V plus D times W must stay in the vector space. What I mean by that, I will explain. So, for example, this is one vector space like R2 space, right? This is one vector space, and this is a vector space if all the combination of any two vector V and W, all the linear combination. So we have this vector V and we have this vector W. Okay, all the linear combinations of these two vectors stay in the vector space. I mean, will stay in this xy plane. Then this xy plane is a vector space. So obviously the xy plane is a vector space because you take any two vector in that xy plane, their linear combination always stay in the xy plane. This is the first thing. Second thing is that the vector space should contain the zero vector. So the xy plane indeed contain the zero vector. So we can say that the xy plane is a vector space. Okay, this xy plane is a vector space. So uh, if we see this definition, that is linear combination C times V plus D times W stay in the vector space, then we can say two things. We can say two things that a vector space is closed under vector addition. So vector space uh, vector spaces are closed under vector addition. And the second thing is vector space vector spaces are closed under scalar multiplication. All right. Because this thing is composed of two things. One is scalar multiplication. C times V is scalar multiplication. D times W is scalar multiplication because C and D are scalars and V and W are vectors. And then we are adding them. So this linear combination is nothing but a composition of scalar multiplication and vector addition. So if I am saying that any two vector in the vector space, their linear combination lies in the same vector space, then what I am saying that vector space are closed under vector addition and vector space are closed under scalar multiplication. That is, you take any two vector, you add them, it remains in the same vector space. And if you take this v vector and scale it, maybe like increase it or flip it or decrease it length, basically scale it in any direction, scale it, then this also remains in the input vector space, right? So this vector space is so this xy plane is a vector space. Okay. So uh, now we will see uh, there are eight rules for vector spaces. I already wrote them down to save time. So the vector space must obey these eight rules. if any space is obeying these eight rules, then it's a vector space. Okay. So the first rule is that the direction, like in whatever order you add the vector, it doesn't matter. So vector v plus w is same as vector w plus v. The second is this v plus w plus z is same as v plus w and plus then z. That is the order doesn't matter. Then the third one, this is an important one. This is important one. It says that there is a unique zero vector such that if you add that zero vector to any other vector in that vector space, then you will get the same vector. So it is zero vector is the additive identity. All right, so zero vector is the additive identity of vector space. Okay, so basically it means that if you add the zero vector to any other vector in that vector space, then it has no effect. You will get the original vector itself. Then the fourth property is that for every vector v in the vector space, there exists a unique. So this is important. Here also the zero vector is unique. You cannot have more than one zero vector in the vector space. If that is the case, then it is not a vector space. Similarly, for each vector v, there is a unique minus v such that if you add the original vector v and the negative of that vector, you get the zero vector. So this is also important that it is the given space is a vector space if and only if there exists a unique minus v. If for a vector v there exists more than such minus v's, such that if we add those to the original vector v, we are getting zero vector, then it is not a vector space. Okay. Then the fifth one is this one times vector v is the vector itself. Here one is the multiplicative identity. One is the multiplicative identity of vector space. So basically, you multiply here one is a scalar. You multiply one with the vector and you get the same vector. The sixth one is you have two scalars, two constants basically C1 and C2. You multiply them both and then you multiply with the vector is same as if you multiply one of the constant with a vector, you get another vector and then you multiply that first constant with the resultant vector. So these two things are same. The seventh property is this one. Basically, this is the distributive property. So C times V plus W is same as C times V plus C times W. The eighth one is C1 plus C2 times V is same as C1 V plus C2 V. So these are the eight rules or properties that the vector space must obey. Every vector in that vector space must obey. If that is the case, then it is a vector space. If any of these properties violated, then that space is not a vector space at all. All right. So just one thing that the rule 1 to 4, the rule 1, 2, 3, 4 is about vector addition, v plus w. If you see, it's all these four rules are about vector addition. Rule 5 and 6 is about scalar multiplication. We are talking about scalar multiplication here. Whereas the last two rules, 7 and 8, these are the important rules. These two rules connects the above rules, rules of vector addition and scalar multiplication. Okay, so this is how these rules are distributed. So it just for you don't need to memorize these rules, by the way. It's pretty simple. It's just that for the completion of I mean for of the topic, I am just covering these eight rules, but these are pretty simple. All right. So now we will see some examples of vector spaces. Okay. I think it will be more clear to you if we go through some of the examples of vector spaces. Okay. First of all, one more thing, that vector spaces is an abstract concept. It's not just about vectors. Vector itself is an abstract concept. So in this case, this vector is a arrow in this xy plane. But vector spaces, you can have vector spaces of matrix as well, which we call matrix spaces. You can have vector spaces of functions as well, which we call function spaces. So, for example, if we have matrices M1 to Mn, then uh, uh, then this span the matrix space. We will see example in a few minutes, but for now I'm just mentioning this. Similarly, maybe you have functions f1 to fn, basically n functions. Then they span function space. Okay, so basically vector space is an abstract concept in linear algebra. So it's not confined to the vectors, which with the traditional vectors we talk. You can have vector space of matrices as well. You can have vector space of functions as well. You can have vector space of any custom object. I mean, it's all you need to have that the vectors or the entity in your vector space need to follow these rules. If it is following these rules, then it's a vector space. All right. So, for example, uh, uh, you have uh, we have these matrices, right? These A, B, C, D, all right, of real entries. So these matrices also form the vector space. Okay, we call it matrix spaces, but we can also call it vector space of matrices. All right. So now we will see some examples of vector spaces. Okay, so uh, let's go with the matrices itself. So we can have vector spaces of matrices. For example, the space R3 cross 3. Okay, and this basically contains all 3 cross 3 matrices. All 3 cross 3 matrices is contained by this, and also the linear combination, the linear combination C times A plus D times B. Here C and D are scalars and A and B are matrices. Okay, these are matrices, 3 cross 3 matrices. All right, are also is also matrix, is also a matrix and belong to R3 cross 3. So we have seen we can see that the linear combination of any two matrix AB belonging to R3 by 3 also belong to R3 by 3. This is what we the property I just mentioned for vector space, right? This one, that CV plus DW should stay in the vector space. Here V and W are the normal vectors, but in this case V and W, A and B are not vectors but are 3 by 3 matrices, but this also forms a vector space. Okay, so if you see that all these 8 properties are going to be satisfied by this R3 by 3. So for example, we will check the first property V plus W. It doesn't matter you add two matrix in what order. If you add a matrix A with B, it is same as adding matrix B with A. All right, so the first property is satisfied. Similarly, you take three matrices A plus B plus C and A plus B then plus C, these two are same. So second property is also satisfied. There exists a zero vector. In this case, that is the zero matrix. There exists a zero matrix 0 0 0 0 0. It's a 3 by 3. Okay, 0 0 0. Right. There exists a 3 cross 3 zero vector, basically this zero matrix, such that if this is the zero matrix, if you add this zero matrix with any other matrix A in the vector space, you get the original matrix A. So the third property is also satisfied. Similarly, for any matrix A, there exists the negative of it. Basically, you just take the negative of all the entries and you will get the zero matrix. Right. Similarly, you multiply one with any matrix A, you get the same matrix. One is a scalar. So 1, 2, 3, 4, 5, all the 5 properties are satisfied. Similarly, you will see that property 6, 7, 8 is also satisfied. For example, if you take a constant C and then multiply it with the addition of two matrices A and B are 2, 3 by 3 matrix. It is same if you do C times a matrix A plus C times the matrix B. Okay. Similarly, you take two constants C1 plus C2 and then multiply with the matrix A. It is same as C1 times A plus C2 times A. Okay. So we have seen that all the 8 properties are obeyed. All the 8 properties are obeyed by by this R 3 by 3, which contains all the 3 by 3 matrices possible of real entries. This is true for complex also, but yeah, here it is R 3 by 3. In that case, it will be C 3 by 3, C 3 by 3 for complex, for 3 cross 3 complex matrices. Okay, but here we are talking R 3 by 3, that is only real entries are there. So R 3 by 3 is indeed a vector space. Okay, so we can say that therefore R 3 cross 3 is indeed a vector space. All right, so it is indeed a vector space because any linear combination of any two matrices in this vector space A and B remains in R3 by 3. So you take any two matrices from R3 cross 3, the linear combination of those two matrices will still remain in R3 cross 3. And also we have seen all those 8 properties are satisfied. So R3 by 3 is also a vector space. So we have seen that vector space is not confined to the traditional vector which we used to think of in physics or maths. It's an abstract concept. Similarly, you can have vector spaces of functions as well. Till the point these properties are satisfied, these 8 properties are satisfied and it is closed under vector addition and scalar multiplication, then it's the set that is a vector space which we call as function spaces. Similarly, it can be uh, vector space could be of anything, maybe of differential operators, differential equations and all. I mean, it is not confined to the vectors which we talk. Just one thing I need to mention in matrix spaces is let us suppose M is a matrix space of this is a vector space of all 2 cross 2 matrices. Okay, so then what is the basis for this vector space? So uh, any matrix in this matrix space is of type A, B, C, and D, right? So for example, every vector space has a basis, right? So for example, this XY plane, this R2 vector space, this R2 vector space has the two basis vector, right? I hat and j hat, right? I hat and j hat. So what is a basis set that any vector v belonging to R2 can be written as a combination of I hat and j hat. So v is nothing but vector v is nothing but some alpha times I hat plus some beta times j hat. Okay, so I hat and j hat are the basis for R2. Similarly, because this M is also a vector space, it's a matrix space. So matrix space is also a vector space of all 2 cross 2 matrices of type this A, B, C, D. So it must also have basis set. So the basis uh, the basis set for M will look like something like this. The first basis I hat, basically this is A1 is 1 0 0 0. The second is A2 0 1 0 0. The third one is A3 0 0 1 0, and the fourth one is A4 0 0 0 1. So the basis set for M is nothing but A1, A2, A3, A4, right? So any matrix, any matrix A which belongs to this matrix space M can be written written as a linear combination of the basis set of the basis set. Okay, so for example, we have this matrix X, which is A, B, C, D. So this X can be written as A times 1 0 0 0 plus b times 0 0 um, b times 0 1 0 0 plus c times 0 0 1 0 plus d times 0 0 0 1. That is x is nothing but a times a1 plus b times a2 plus c times a3 plus d times a4. Okay, so a1 a2 a3 a4, this set is the basis set for M. Okay, so combination of these four matrices can produce any 2 cross 2 matrix in M. All right. Similarly, if we have a matrix space, let us suppose M2. And then let us suppose this is M1. Okay, if we have the matrix space M2, which is nothing but uh, vector space of all 2 cross 2 upper triangular matrices, then the basis set, then the basis set for M2 is, because it's an upper triangular matrix, so the basis set is A1, A2 and A4. All right, A3 is not required this because this is a collection of upper triangular matrices, right? So A1, A2 and A4 is the basis set for such matrix space M2. All right. Similarly, if we have lower triangular matrices, then it will be A1, A3, A4. A2 is not needed. Okay. And similarly, A1 and A4. Just A1 and A4 is the basis set for all diagonal matrices. All right. And let us suppose we have another vector space of all symmetric matrices, symmetric matrices. Then the basis set for M3 is A1, A4 and A2 plus A3. Right, A1, A4 and A2 plus A3. Okay, so the dimension of this symmetric matrices vector space is 3. So I will, in the next lecture I will mention what is dimension, but right now you can mention that this is 3. Dimension of M2 is also 3, whereas dimension of M1 is 4. All right, because we have these four bases in the basis set. Here we have three basis metrics in the basis set. All right. Yeah, just one more thing that I need to talk is I'm mentioning space, vector subspace, metric space, function space. So I didn't define space. So what is space? So the space basically means that all linear combination of the vectors or matrices or function whatever stay inside the space. Okay. So space, what it mean by space is that all linear combinations all linear combinations of vectors or matrices if you're talking about matrix spaces, or functions if you're talking about function spaces, or anything else, stay inside this space. All right, so we have seen matrix spaces as well. Similarly, we have function spaces. So for example, if we have this function y equal to c times e to the power x, where c is any constant, then this also forms a vector space, and it forms a vector space of functions. We call it function spaces. Okay, so vector spaces are not confined to just the traditional vectors. It is it's a more abstract concept. All right, so for example, if I show you this visualization I have. All right. So for example, if I take any two vector in this space, for example, this v1 and let us suppose I take this v2. All right. So if I take any two vector, this is v1 and v2. All right, these are two vectors in this R3 space v1 and v2, and if I add them, this the resultant vector is also in this space R3, right? So this is the two-dimensional representation v1 and v2. If I added them, I got this v3. So this is nothing but a vector space. Why? Because a linear combination of any two such vector v1 and v2 is inside the space only. So this is a vector space, and also the zero vector is also belonging to this R cube. So this R cube, this entire XYZ volume is nothing but a vector space because it follows those properties of vector space. Okay, so I am ending the video here only because vector spaces will further take 15 to 20 minutes, so I don't want to stretch this video long. So I will cover vector subspaces in the next video. So if you like my videos, then please share my videos with others, subscribe my channel, share my channel, and this really motivates me. So yeah. See you next time. Bye.